All right, gang, stat 1150, two variable statistics. Just want to put up a video here, kind of twofold. First of all, I want to review a little bit of what we've covered in previous videos. And then the second thing I want to do, there are a couple of problems that I want to work that are on my math lab that are going to be similar to some of the things that you're going to encounter on your homework assignment or assignments. I want to review just a little bit and include a little bit of new information as well. First thing, we would, if we have two variable statistics, now guys, when you see that, what you typically think about is you have two measurements from each subject or each observation. So we have an X value and we have a Y value, hence we call it two variable statistics. We like to come in and still look at the variables independent of one another and report the means and the standard deviations, possibly even look at histograms for each one and box plots. But then we want to change our focus to look at the relationship between X and Y. For example, if as X increases, what does the Y typically do? So we want to do that. And the very first thing that we would want to perform in that evaluation is to visualize the variability. Well, guys, we're going to visualize the variability with something called a scatter plot. The guys, a scatter plot is nothing more than a picture that gives us the relationship between X and Y. Now, this X that we focus on is almost always the first value that we get. Now I say almost always because sometimes your data sets could have an X value that's to the right of the Y, but we have to make adjustments according to the goal of the relationship that we are evaluating. Well, nevertheless, this X value comes with different names. Sometimes we call it the predictor. Sometimes we call it the explanatory. And sometimes we call it the independent variable. Okay? That doesn't seem to be as clear as I would like it. Let me see what I can get going on here. Okay, I think it's a little clearer. Now, on the same token here, if we have the X value called the predictor, then we typically call the Y value the predicted. If we call the X value the explanatory, then we call the Y value the response. And if we call the X value the independent variable, then we call the Y value the dependent variable. Okay? Now, the purpose of a scatter plot, if we think about this, the purpose of a scatter plot is threefold. We want to look at the trend. Do we have a positive or negative relationship? We want to look at the strength. And we want to look at the shape. Now, for this class, shape is just going to be linear or nonlinear. So, if I have a relationship between X and Y that looks something like this, the trend would be positive because it has an upward tendency. The strength would be strong because if I visualize a straight line down the central focus of the data that we've plotted, I don't have a lot of vertical move, a lot of vertical variability away from that line. And I would call the shape linear because again, kind of the central focus, the overall pattern of the relationships seems to follow a linear tendency. So, this is just review. We've talked about all this stuff in previous videos. So you guys should be experts at that by now. Now, in statistics, As you should know by now, we love to look at pictures, but ultimately we want to quantify important characteristics. And the important characteristics that we want to quantify here is the relationship. So we want to be able to summarize the relationships where we want to quantify the relationships. Now, one thing that we typically do, and this is from the Scatterplot, is we report R and R squared. R is the correlation coefficient, falls between -1 and +1. So it summarizes the linear tendency. And the R squared is just typically a percentage that even, in my opinion at least, better explains the relationship, kind of quantifies the relationship that we visualize in a scatter plot. Something else we do is we fit a linear model. And what we do in the linear model is we seek to predict a value. So we call this the predicted Y. Can be found by taking a certain value times X times a certain value. Now I'm using boxes there because depending on the technology that you use, even if you use the TI-84, this right here can either be B or A. This could be A or B, and I'm going to show you that in just a second, how it can certainly lend to itself to a lot of confusion. So, guys, the purpose here is to ultimately get into to larger data sets, but I just want to illustrate very, very quickly, if we had a smaller data set between X and Y. And I don't know, I'm just making this kind of up as I go. So let's say we have 0, 1, 2, 3 as our X's and 1, 3, 5, 9 as our Y's. I would see no reason really to use R here. Again, the goal number 2 of this video. I would probably just go into my calculator, which I've already done. And I would type, let me get this where you can see it, type the numbers into L1 and L2. So now I said earlier that our X's come first. It's easier if you make these X's first. I think it lends itself to less confusion, and put your Y values in second. Guys, notice that this 0 and 1 must be on the same line because this 0 and 1 represents the first observation. This 1 and 3 represents the second observation. So for this very first student or tree or dog or cat, whatever it is, we've collected an X value of 0 and a Y value of 1 on that particular subject. Guys, they must be on the same line when you put this in your calculator. So guys, from there it's going to be very simple. Go to Stat, decide what you want to use so you can be consistent with it. If we come to Calc, you can see that it can come down to number 4. It says linear regression. In this situation, the A turns out to be the slope and the B is the intercept. Just so the Texas Instrument calculator folks can just confuse the heck out of you. If you come down to number 8, you'll see that if you run this model, that the value you get for B is your slope, where it was the intercept up here, and it was the value for A is the intercept, where up here it was the slope. I think the best way to keep to at least minimize the confusion here is to always use the same calculator command. So guys, I always teach this one. Come over to Test and go to Linear Regression T-Test. L1, L2 are X's and Y's. Frequency should be 1. Beta and rho, that's for a class level higher than this one. Y1 is our regression equation. Let me show you how to put that in. I've shown you in a previous video. But if you don't have a regression equation, there's Y1. Let me show you how to do that. You can come to Variables. You can go over to Y Variables, hit Function, and select Y1, which is the default, and hit Enter. Now it's going to put that Y1 is the regression equation, so when you go back to your scatter plot, it's going to have the line of best fit drawn on the scatter plot, which is kind of cool. All right, gang, calculate. Don't forget, what's the format? The format here is our B is the slope, our A is the intercept. So don't worry about this, don't worry about that, not applicable to this class, degrees of freedom. Come on down, A is 0.6 and B is 2.6. But first of all, I want to look at the R and R squared. So the R is 0.98, so I could the R squared, which is always presented as a percentage, is 96. So it's either going to be 5 or 6. I have to go to that fourth digit to see if this goes up to a 6. Since this is 5 or bigger, it does. So this will be 96.6%. And my B is 2.6. And my A is 0.6. So based on the data that I've collected, if I have future data that I would like to predict the Y from the given X, then I would use this model to do so. Okay? Now, I told you earlier that if we do Scatterplot, now guys, all we got to do is got to come up here. Well, I'm sorry. We need to go second function stat plot on. And guys, again, this is all review. I've done this in previous videos, so you might say, well, you're going a little fast. Well, I've done this before. Zoom 9, and you'll see that the line of best fit is on the scatter plot. Now, the reason it is again, because of that Y1 right there. All right? Now, sometimes life isn't as simple. And what I want to do now is I want to get out of this, and I want to go to Google Chrome, and I want to go to, let me make sure I'm still connected, yeah. I want to go to my math lab and take a look at a couple of problems. So here's something that I put up. I don't know if you'll see this or not, but there's, aside from assignment 1, 2, 3, 4, 5, or whatever may be there for the class that you're taking, I created an assignment here which I will delete after this. So if you see that, do not do, okay? So I've gone into preview. And if I hit preview, let's see what goes on here. I can go into the assignment. Yeah. What says the data shown in the accompanying table are the number of years of formal education of the fathers and mothers of sample 29 statistics students at a small community college in an area with many recent immigrants. You know, in higher education, mother and father's education level can play an important role in predicting success trends of students who are currently in college. So the data shows suggest a linear trend, complete parts A through C. Now, when I click the icon to look at the data, you can see that there's quite a bit there. So right here, this particular student, their father went to school 4 years, their mother went to school 4 years. This particular student, their father went to school 11 years, their mother must have gone to something, I'm not sure whether they're calling formal education kindergarten, so 13 would imply to me that has at least 1 year of formal education. You can come on down here and see 4 and 1. So, you know, I could, if I want to, I can sit down with my TI-84 and I can calculate, or I'm sorry, I can type all these fathers into L1 and mothers into L2. I could do that. Chances are, though, as sloppy as I am with typing, I probably would make a mistake somewhere. So I'm going to seek out something easier. So I'm going to click this right here, and I'm going to open this up in Excel. So guys, I'm going to click that. I'm going to make it a little larger so you can see. And, you know, this kind of annoys me over here where it's got father, mother. So, guys, I'm going to come over here and start a new data set because I don't want to get into R and have any chance of any kind of mistake. You might say, well, that's being kind of anal retentive. Well, guys, when you do this for a living like I do, we can't have mistakes. And I don't know how R would handle that. I think it would handle it just fine. I don't know. I think it probably would. All right, so make sure I did a good job. Yeah, to have the same. Going to delete what I've got. Delete what I've got. And gang, I always like to come in and insert and just put ID. And I put a 1 there, and I'm going to start the equal 1 plus that. I think there's a renumbering option here. Going through this kind of fast because I've illustrated it before. And you can always stop. So I have 30 mothers and fathers. So because I have to get this right, I'm going to go back and make sure. Wait a minute, I have, did I say 30? I have 29. Go back and make sure that I have, yeah, so sample of 29 statistics students. All right, gang. What I would now do is come in and do a save as. I would call this something very simple like data. I would save it to my desktop, and I'm going to save it as a .csv. Hit continue. It's saved. I'm going to close it down. I don't need it anymore. And now I'm going to get rid of this, and I'm going to go get my data. All right? So, gang, what I'm going to do now is I'm going to open up R, which we've talked about before. I'm going to set my working directory, which we've talked about before. Now, I'm glad this happened. I've been going back and forth between Windows and between my PC and my Mac, and I'm going to pretend that I don't remember how to set the working directory. I do, because I do it all the time. So I'm going to get the working directory, and I can see that my format has to be like that, but after my name I have to have desktop. So I'm going to set the working directory. Now I'm going to go get my data, and I'm just going to call it data when it imports it in here. So I'm going to use the read.csv. I was at somebody's office the other day, and they said, "Oh, come meet my cat." And I'm like, "Well, what's your cat's name?" And they said, "What's cat?" Okay, that's easy to remember. Guys, I keep it simple like that. I don't name my cat cat because I don't have a cat, and I don't name my dog dog. But my data set is data.csv on my desktop on my computer. So why not keep it simple and just call it something very simple once I get it into R. So guys, I got to attach the data, and I always like to look at the names of the data so I know exactly how to type the variables when I want to access them. Now, let's go back to our question, and we've got to be kind of careful here. What we're trying to do is we are trying to predict the mother's education. So that tells me that the mother's education has to be Y. So I want that to come second when I do my commands in R. So, and it came second, so that worked out okay. So if I want to do for example, the correlation between father and mother, I can see that we have a correlation here of 0.539 actually. And if I want to do R squared, then all I would have to do is get that and square it, and I see that we have a R square of 29.0%. But the purpose of this question is a little bit more complicated we want to create the regression equation for predicting mother's education from father's education. So what I would do in R to do that is I would call this my model. And I would use the command LM, which is linear model. And I would put the mother first. I put my Y value first, tilde, father. So the general form of this is to put your Y first and put your X second. But since I have put Y in here as mother and X in here as father, then I have to use the names of the variables that R is seeing. Now nothing happens if you did this correctly and you're like, oh my gosh, what did I do? I didn't get my answer. Well, guys, all you got to do is just type model and you get your numbers. Now, father here is your X, so the value that goes with father is your slope. So guys, our slope is going to be 0.51. Now I need to go back to R and see how many places it wants us to report the answer. So it says 2 decimal places. So gang, I'm going to put this down. I'm going to write it on a sheet of paper that my slope is 0.52 and my intercept is 4.10. Now, this right here rounds up to 1 because this digit is 5 or bigger. So I'm going to go back in, put this in R. So the slope must go with the X, which is father's education, which is 0.52. And the intercept is 4.10. Check the answer. It's going to be right. And we'll go on to the next. Now, using the found regression line, find the predicted number of years for the father who has 12 years of education, round to 2 places. All right, so what I need to do here is I need to take the 4.10 plus the 0.52 times the 12. It was 12, right? I get sidetracked easy. Got 12 years of education. So what I get there will give me 10.34. All right, so 10.34 is going to be right. Check the answer. It's all good. Now, using the found regression line, predict the number of years for the mother if the father has 4 years of education. Well, I've already done it here, so I'm just going to hit the up arrow. And the only thing I need to do is change the 12 to a 4. And I get 6.18. Again, complete confidence, it's going to be right. Go to the next one. Now the next one says, find and report the regression equation for predicting the father's education. Now, father's education now becomes the Y because that's what we're predicting, so we're kind of reversing the model. And let's notice something. Notice when we do this with the correlation, notice what happens. So instead of putting father first, we're going to put mother because it's our X. We're predicting father's education. But guys, when you'll notice that when we do this, that that the correlation stays the same. And when we square that value, it's going to stay the same too. So when we switch the value that we're predicting, the correlation doesn't change. The coefficient of determination, R squared, doesn't change, but the model will change. Now, so what do we need to do here? We're going to create another model, so I'm just going to go up and get the form. And I'm just going to call this model number 2, just in case I need to go back and get the first model. But this time I want to predict father from mother. Again, guys, whatever we're predicting always goes first. Whatever we're using to predict goes second. So model 2. So we can see that the slope now is 0.56. So I'm going to write that down. And the intercept is 3.44. So depending on what we're predicting, the slope and the intercept turn out to be different. So check it. It's going to be right. Now, what if you're using your calculator for this? Now let's go back over, and I want to demonstrate what you would do. You know, if you're just focused on this calculator and you're just not going to allow me to teach you anything with R, it's going to hurt you ultimately in your grade. But if you want to dig your feet in, then that's okay with me. But if you really just want to focus on the calculator, because that's what you'll be using mostly on your test, if I want to run the reverse, let's say I've got the values in my calculator, but I want to reverse like I did mother and father versus father and mother. Well, all I'd have to do is come in here and change L1 to L2 and L1 to L2 and L2 to L1. This would accomplish the same thing as changing the Y tilde X to just reversing reversing the variables. All right, gang. Let's let me get out of this. Get back to. All right, so let's go back to use the found regression line to predict the father's years for the father if the mother has 12. Well, that's again going to be really easy. So we'll have 3.44 plus 0.56 times 12. So 10.16. Use the found regression line to predict for 4. It's kind of cool when we write it out like that. We can just go up and put a 4 in. So 5.68. Now there are other ways to do that on R, and I was tempted to show you that, but you know, again, I'm teaching now, so sometimes when I do and teach, it's different. Okay. Now, what phenomena does this demonstrate? Regression toward the mean, because the regression line is used to make predictions beyond the range of data. Well, guys, if we look at our data, do we have 12 and 4 within the scope of our data? Well, let's just take a look at the. So we range from 0 to 16, so it's within the scope. We have no extrapolation going on here in 0 to 14. So the two values that we use to predict 4 and 12 are both within the range of our data, so we don't have any extrapolation going on here. So that's not an issue. Regression toward the mean, because the values are far from the mean, leading the response are closer to the mean. So guys, what do you think here? So extrapolation is not an issue because the values for the predictor are rather far from the mean, lead to response that are closer to the mean. So what do you think? Regression toward the mean? So what do you think? Read it through. Hesitating here. Because values for the predictor that are far from the mean are such that are closer to the mean. Let's go with this one. Pretty obvious, wasn't it? All right. question 2, let me see what I've got going on here. Assume that in a political science class, a teacher gives a midterm exam and a final exam. Assume that the association between midterm and final scores is linear. Okay, summary of statistics. So we have our value. Now guys, I'm going to go split screen here so we can see a couple of things, and I want to bring this up and get a new sheet of paper. All right, gang. Shoot, I can't. All right. So what do we have here in summary statistics? We have that the R value is 0.70. We have a sample size of 20. And we have some summary statistics for the midterm and the final. So we have that the mean is 73 and 73. And we have the standard deviation is 10 and 10. Okay, well, that's very interesting. According to the regression equation for a student who gets a 94 on the midterm, what is the predicted final exam grade? What phenomena does this demonstrate? Okay, guys, we don't have the data here, so what we have to do is we have to kind of crunch it out by hand. And we can see that we can always find the slope by taking the correlation times the standard deviation for y divided by the standard deviation for x. Now, in this, the reason I hesitated is we didn't define what was x and which is y. Typically speaking, whatever you're trying to predict, which would be the midterm here, would be your y, and of course the value that you're using to predict is your x. So gang, we're going to do a simple correlation is 0.70. The standard deviation divided by the standard deviation. Actually, it would be this one divided by this one, but it doesn't matter in this case. So our slope is 0.70. Two places, right? Yeah. Find the y-intercept using the equation a equals y bar minus, so our intercept can be found by taking the mean of my y's minus the value I just found times the mean of the x's. So guys, the mean of the y's is 73 minus 0.70 times 73. And we get 21.9. Now guys, my regression equation will be y hat (21.9). All right. So my intercept is 21.9. Well done. Excellent. We like that. Now write out the following equation. So let's probably done over here, so let's go back to the full screen. Write out the predicted, how I've used predicted finals to predicted y. And so predicted final is going to be 21.9. And my midterm is 0.70. Use the equation to predict the final exam score for a student who got 94. Now I'm going to go back over here. So we have an 87.7. So it says round to the nearest integer. So 87.7 would round to an 88. Your predicted final exam grade should be less than 94. Why? Well, do we have any So regression toward the mean because the student's predicted final exam score is closer to the mean than was their midterm score. Regression toward the mean because the student's predicted final exam score is further from the mean. Extrapolation because the predicted score is lower than the midterm score. Extrapolation because the score of 94 is outside the range of data. Well, guys, the 94 doesn't appear to be outside the range of data because of our standard deviation. So what do we think here? The predicted is... So what's going to happen here is our 94, our 88 is being pulled toward the mean because the predicted score is closer. So I'm going to go with this one right here just to see what happens. All right. And it makes total sense, doesn't it? The predicted score is closer to the mean because, guys, these scores are always going to regress toward the central tendency. This is the obvious choice. Well, I don't need a similar question. So, gang, that's about all I got for you. Midterm exam coming up pretty soon, so there's going to be more information on that very, very, very soon. So, it's getting ready to get fun. All right, take care.